Hey guys, let's talk about simple properties of vector addition. We say that vector addition is commutative. What exactly is it? Let's say that we have a vector A, right? So that's vector A for me. And let's suppose I walk from here to here. Let me name it to be A and B. All right, that's vector A. Now from here I walk from another distance from B to C. Okay, that's C for me, the point C. And let me call this to be vector B. Now, from where to where did we walk in the question? So I can say that the actual displacement is from A to C. So that is vector A plus vector B. So we understand that. Very simple, right? Now, what if I don't choose to walk from A to B, but actually draw another vector which is equal to vector B here? So it means I'm drawing another vector like that. Okay. So that, let's say that that's point D for me. Now, I choose to walk from A to D, which is actually vector B. Why? Because this is a free vector. I'm just shifting it here. These two are equal vectors. Fine. I walk from A to D. From here, I walk from D to C. Now, that's vector A for me. Why? Because these two guys are equal. Beautiful. So, whether I walk from A to B, from B to C, where am I going? From A to C. So, I can write that displacement as A plus B. Okay. Now, what if I walk from A to D? It means I'm actually walking vector B. Then, from D, I'm walking here. So, that's the addition now. So, I can write vector B plus A. Overall, both the cases I'm actually walking from A to C. So I can write that as vector AC. So that makes simple sense that yes, vector addition is commutative. Let's talk about the associative law, guys. Well, guys, let's talk about the second property, the associative property. We have three vectors here, vector A, B, and C. Now, if I add these vectors in two different fashions, that is, I keep the vector A just like that. Now I add vector B and C first. It means that's vector B and that's vector C. So if I add these two guys, I do get another vector, which is this guy. So I can just write this guy to be vector B plus vector C, because I'm walking from here to here and from here to here. That's all about it. Now I'm adding vector A plus BC. So what do we get? Let me change the marker. So if I add that, I do get this guy, which is basically vector A, that is this guy, plus vector BC. So this is nothing but vector A plus vector B plus C. All right, that's what it is. Now, what if I do the same addition but in a different way? Let's suppose first we add A plus B now. So it means I'm adding vector A and vector B. So what I'm getting is this guy. So let me draw it with a dotted mark. Yeah, dotted line basically. So that is the vector A plus B for me. This dotted line here is nothing but vector A plus vector B. Good enough. With this, I'm adding vector C. So I'm adding vector C with this. So now what I'm getting? I'm adding this. Let me draw another line here so we can differentiate. There's the pink and the green line together. So that line here for me is A plus B. With that, I'm adding vector C. So overall, I'm going from here to here, then from here to here. Overall, I went from here to here. It means associative law is satisfied. Whether I do it like this, whether I go from A, then I add B and C, I'm reaching D here, right? Or I add A plus B first. It means I go from A to C first, then from C I go here. I get the same thing. Very simple, guys. Third property is simple, guys. It says that vectors do follow additive identity. Basically, I have a vector A, and with this I'm adding nothing else. So what do you get? Vector A plus a zero vector. A zero vector is a point. All right, so I get what? I do get our vector A itself. So that's pretty easy. Now, what exactly is the fourth one? It says vector A plus negative A. It means I start walking from here. I go at this point. That's vector A for me. And I stop. Again, I come back to the same place. So where do we go? Nowhere. So it means vector A plus. Okay, when I come back, I do write as minus vector A. So vector A plus minus vector A is what? Basically a zero vector. It means I came back to the same point. Works. Now, the last property is very interesting. For this, I would definitely want to use the graphic diagram. This is interesting. It says the modulus of vector A plus B is always less than or equal to the modulus of A plus vector B. Now, if I have to even draw that, let's suppose that's vector A for me, and let's say that's vector B. Now, if I add vector A and B, what I get is this guy. This is vector A, and this is vector B, A plus B basically. Now, if I say this is like, say, A 4 centimeters, let's say this is 3 centimeters. Can this length be 7? Look at that, this A, B, and C. If I walk from A to B, that's 4 meters, and from here to here is 3 meters. Do you think so AC is 7 meters? Never is possible unless it is a straight line. So in any triangle, I cannot say that third side, one of the side is equal to the sum of the other two, unless it is like this. I go from A to B, which is 4 centimeters, and from here I walk 3 centimeters, right? So now if I say this is A, B, and that is C, if this is 4 and this is 3, then I can say that this guy can be 4 plus 3, which is 7. So in this case, I can write that is modulus of vector A is 4 in this case, and let's say that's vector B for me, and modulus of vector B here is 3. But in this case, I can write, yes, of course, this is A plus B. Then I can write the modulus of vector A plus vector B can be 7. In this case, I can write that modulus of A plus B definitely is equal to modulus of A plus modulus of B, all right? Now, in this case, yes, if it is collinear. In this case, if this A and this B, it is impossible that this guy would be equal to these two guys. In this case, the modulus of vector A plus vector B should always be less than modulus of vector A plus the modulus of vector B, because one side in a triangle can never be equal to the sum of the other two sides in a triangle, but in a straight line it's possible. So let's watch this in a graphic diagram. Well, yes, let's talk about the third property with the graphic diagram. In this case, I can see that here I have vector AB, which is whose modulus is 4, that's vector A for me, and that's vector B whose modulus is 2.83. Now when I add these two guys, I do get a vector AC. Right, that's the resultant. That is the modulus of vector A plus vector B is nothing but what? That's nothing but 6.32. Now that line is what I'm talking about, vector A plus B. Now if I see that vector A plus B should always be less than or equal to vector A plus vector B, I can see that in this case, yes. Here in this case, this guy is 6.32. It makes sense, right? And I can see that this is 4 and this 2.83, and I can see that 6.32 is less than 6.83 always. Now what if I move the point C here? Look at that. I'm moving the point C here. I can see that the modulus of A plus B, which is nothing but the vector AC in this case, is 5.83. And if I add it with 4 plus 3.16, I get 7.16, which is definitely greater than 5.83. So it means the modulus of A plus B is always less than this the sum of modulus of A and modulus of B. Makes sense, isn't it? Now when is it actually equal? So if I move this point in such a way that it comes here, now look at that. When I see that the modulus of vector A is 4 and the modulus of vector B is 4, then the modulus of vector A plus B from here to here, which is the vector AC, is 8. At this point I can say 8 is equal to 8. Makes sense? Now anywhere other than this, I can say this guy is always less than 8.12. Yes, of course. That exactly is the property, guys. This can happen only in the case that it is collinear, if these two vectors are collinear. All right. So I can say any other condition, I don't say it's possible. That's all about it.